Have you ever stopped for a moment and asked yourself, is there anything in the entire universe that is truly still? Not slowly moving, not drifting quietly, but completely motionless. Inside that glass, billions of water molecules are crashing into each other trillions of times every second. Stillness is just an illusion. Right now, the Earth beneath you is spinning at 1,000 miles per hour and orbiting the Sun at 67,000 miles per hour. Our entire solar system is racing through the galaxy at a staggering 825,000 miles per hour. In just the last minute, you have already traveled tens of thousands of miles through the vastness of space. Everything around you feels perfectly still, but in reality, motion is the only constant in the universe. This realization leads to a strange and fascinating question. If we are moving through space at hundreds of thousands of miles per hour, why don't we feel it? Why doesn't the coffee spill out of your cup? When I shake a glass in my hand, the water sloshes everywhere. But the Earth is racing through space at enormous speed, and yet oceans remain calmly in place. Why don't we feel a cosmic wind rushing past our faces? Why are we not thrown violently against the walls of our homes? To answer that mystery, we have to go back several centuries to one of the great thinkers in the history of science, Galileo Galilei. Galileo discovered something that completely changed our understanding of motion. He realized that nature does not actually care how fast something is moving. What nature cares about is whether the motion is changing. This idea is called inertia. It is one of the most fundamental laws of the universe. According to this law, an object moving at a constant speed in a straight line will continue moving that way forever unless something interferes with it. The universe does not require a constant push to keep something moving. In fact, motion is the natural state of things. Think of it this way. Imagine sitting on a perfectly smooth train traveling at a steady speed. Inside the train, everything behaves normally. You can pour a cup of tea, toss a ball to a friend, or walk down the aisle without any difficulty. As long as the train moves smoothly, you feel as if you are standing still. Only when the train accelerates, slows down, or turns sharply do you notice the motion. The Earth works exactly the same way. Our planet spins smoothly. It orbits the sun smoothly. And our entire solar system moves through the galaxy smoothly. Because these motions are steady and consistent, we feel nothing unusual. In other words, there is no absolute state of rest in the universe. Stopped is simply a word we invented to describe moving at the same speed as the environment around us. When you say you are sitting still in a chair, what you really mean is that you are moving at the same speed as the Earth beneath you. Now we have established something incredible. Everything is moving. The atoms in a glass of water are vibrating. The Earth is spinning. The planet is orbiting the sun. The sun is drifting through the galaxy. But this discovery creates an even deeper question, the kind of question a curious child might ask. And so we must ask ourselves, why doesn't it stop? In our everyday experience, things always come to rest. If you slide a piece of chalk across a table, it slows down and stops. If you push a ball across the floor, it eventually loses speed and rolls to a halt. If you turn off the engine of a car, the vehicle gradually stops moving. Our daily world teaches us that motion fades away. Energy seems to run out. But when we look at the universe, we see something completely different. The atoms in matter have been colliding with each other for billions of years. They have not grown tired. They have not lost their energy. The Earth has been spinning for more than 4 billion years. No one is pushing it. No cosmic engine is keeping it turning. So what keeps everything going? This question forces us to examine something even more fundamental than motion itself. To understand why the universe never seems to slow down, we must explore the nature of energy. Energy is the currency of motion. It is what allows atoms to vibrate, planets to orbit, and stars to burn. And for a long time, scientists believed that if you removed all energy from a system, if you cooled everything down to the lowest possible temperature, motion would finally disappear. In theory, if we could cool the universe all the way down to absolute zero, the coldest temperature imaginable, everything should freeze into perfect stillness. In that state, even the atoms would finally stop vibrating. Particles would stop moving. Reality itself would become silent. But when scientists began studying the deepest laws of nature, they discovered something astonishing. Even at absolute zero, the universe refuses to sit still. This discovery shocked physicists because it challenged one of their oldest assumptions. For centuries, scientists believed that if you removed every bit of heat from a system, motion would eventually disappear. Heat, after all, was understood as the movement of particles, so logically, if heat vanished, movement should vanish with it. The universe would freeze into perfect stillness. But nature had something very different planned. Before we reach that strange conclusion, we first need to understand what heat actually is. For thousands of years, even brilliant philosophers misunderstood it. They believed heat was a substance, a mysterious fluid that could flow from one object to another. This imaginary fluid was called caloric. If something contained a lot of caloric, it was hot. If caloric leaked away, the object became cold. It sounded reasonable. It even matched everyday experience, but it turned out to be completely wrong. Modern physics revealed something far more fascinating. Heat is not a substance at all. Heat is simply motion. It is the movement of atoms and molecules. To understand this, imagine zooming in on the air right in front of your face. The air may feel calm and invisible, but at the microscopic level, it is incredibly active. The air is made mostly of nitrogen and oxygen molecules, and these molecules are not floating peacefully. They are racing around like tiny bullets. At room temperature, these molecules move at roughly 1,000 miles per hour. Every second, they collide with your skin, bounce off nearby objects, and slam into one another countless times. If these molecules were the size of baseballs, the air around you would look like a chaotic storm of projectiles flying in every direction. And yet you do not feel it. Why? Because the molecules are extremely small, and they hit you evenly from all directions. Their impacts balance out, creating the gentle pressure of the air we breathe. Now consider what happens when something becomes hotter. When you heat an object, you are not pouring a magical substance into it. You are simply giving its atoms more energy. That energy makes the atoms move faster. They collide more violently and more frequently. When you accidentally touch a hot stove, the pain you feel is not mysterious heat entering your finger. What actually happens is far more mechanical. The fast-moving atoms in the hot metal crash violently into the atoms of your skin. These microscopic collisions damage your cells and trigger the sensation of burning pain. In other words, heat is just a furious dance of atoms colliding with one another. But this explanation leads to another interesting question. Gas molecules move freely through space, so their motion is easy to imagine. But what about solid objects? Look at a wooden table or a metal chair. They appear completely still and rigid. The atoms in a solid cannot move around freely like gas molecules. So how can a solid object have temperature at all? The answer lies in the structure of matter. In a solid, atoms are arranged in a crystal lattice. Atoms occupy fixed positions, connected by invisible forces like tiny springs. When warm, they vibrate in place. As heat increases, vibrations grow violent until the bonds break and the solid melts into a liquid. But what happens at absolute zero? Classical physics predicts that all motion should stop completely. The universe should become silent and frozen. Yet experiments show atoms never truly stop. Even near absolute zero, nature fights against stillness. Motion does not disappear. To understand why, we must leave classical physics behind and step into the strange and impossible realm of quantum mechanics. One of the key discoveries in quantum mechanics came from a physicist named Werner Heisenberg. He uncovered a rule that completely changed our understanding of motion and position. This rule is known as the uncertainty principle. Now, the name itself often confuses people. It does not mean that everything in the universe is uncertain or unpredictable. The principle is actually very specific. It states that there are certain pairs of properties in nature that cannot both be known with perfect precision at the same time. The most famous example involves a particle's position and its momentum. Position simply means where the particle is located. Momentum describes how fast the particle is moving and in what direction. According to Heisenberg, it is impossible to measure both of these properties with perfect accuracy simultaneously. If you focus on measuring the exact position of a particle, the uncertainty in its momentum becomes larger. If you measure the particle's momentum very precisely, its position becomes uncertain. The two quantities behave like opposite sides of a seesaw. When one becomes precise, the other becomes fuzzy. This is not a limitation of our instruments or our technology. It is a fundamental rule built directly into the fabric of reality. Now think about what it means for something to be perfectly still. When we say an object is completely at rest, we are making two very precise claims. First, we are saying we know exactly where the object is located. Second, we are saying we know exactly how fast it is moving, which would be zero. But the uncertainty principle tells us that this combination is impossible. Nature does not allow both perfect position and perfectly known momentum at the same time. If we try to pin a particle down to a specific location, forcing its position to become very precise, its momentum must become uncertain. That uncertainty does not mean the particle might be moving or might not be moving. It means its motion fluctuates wildly. The particle begins to jitter, jump, and vibrate in unpredictable ways. Imagine trapping a tiny particle inside a box. At first, the particle moves around freely. Now suppose we start shrinking the box, making it smaller and smaller. As the box becomes tighter, we are forcing the particle's position to become more and more precise. According to the uncertainty principle, the particle's momentum must increase to compensate. The smaller the box becomes, the faster the particle begins to move. It slams into the walls more violently. The energy inside the box rises dramatically. In other words, when we try to trap a particle into perfect stillness, the laws of quantum mechanics fight back. This is not a limitation of our instruments or our technology. It is a fundamental rule built directly into the fabric of reality. This principle is actually the reason matter exists at all. Consider the structure of an atom. At the center sits a tiny nucleus containing protons and neutrons. Surrounding it are electrons. These electrons carry a negative charge, while the nucleus is positively charged. Opposite charges attract each other. Classically, we would expect the electrons to spiral inward and collapse into the nucleus. Chemistry would not exist. Matter itself would collapse. But the uncertainty principle prevents this disaster. As an electron moves closer to the nucleus, its position becomes more tightly confined. The uncertainty in its momentum grows larger, forcing the electron to move faster and faster. This motion prevents it from falling into the nucleus. Instead of collapsing, the electron forms a cloud of probability around the nucleus. The atom becomes a stable structure. So even at absolute zero, when almost all energy has been removed, atoms still possess a small amount of unavoidable motion. This leftover energy is known as zero-point energy. It is not heat in the ordinary sense. You cannot use it to warm a room. But it represents the lowest possible energy state that matter can have. And even that state includes motion. We can observe this strange behavior in certain substances, such as helium. When most materials freeze, helium behaves differently. Even close to absolute zero, it stubbornly refuses to solidify. The atoms remain in a liquid state, constantly moving. Nature would rather keep the atoms moving than violate the uncertainty principle. Motion is required for matter to exist. The particles that form our bodies, the air around us, the ground beneath our feet, all of it survives because perfect stillness is forbidden. But so far we have only looked at motion on small scales. Now we must ask a much larger question. What about the universe itself? Because it turns out that not only are the particles moving, but the very fabric of space is moving too. Up to this point, we have been talking about motion in the things inside the universe, atoms inside matter and planets around stars. We quietly assumed space itself was still. We imagined the universe as a giant stage where actors move, but the stage remains fixed. For a long time, even the greatest scientists believed this. Albert Einstein originally thought the universe was static and eternal. He believed space was like a rigid container that simply held everything inside it. But nature had another surprise waiting. In the 1920s, Edwin Hubble discovered that distant nebulae weren't just gas clouds, but entire galaxies far beyond our own. He found their light was redshifted, meaning they're moving away. Just like an ambulance siren drops in pitch as it passes, light waves stretch and appear redder as galaxies recede. This happens because space itself is expanding. Imagine dots on a balloon. As you blow it up, every dot moves away from every other dot. No matter where you are, the universe is stretching in every direction. That is the incredible discovery of our expanding cosmos. Galaxies are not racing through empty space. Instead, the space between galaxies is stretching. This expansion began 13.8 billion years ago. The universe started in an incredibly dense and hot state. Since that moment, space itself has been expanding outward. But the story doesn't end there. Astronomers discovered something shocking. The expansion isn't slowing down, it's speeding up, pushed by a mysterious force called dark energy. Not only is the universe expanding, but events happen in a particular direction, from past to future. Why does time flow in only one direction? A glass can fall and shatter, but we never see the pieces jump back up to rebuild themselves. Physics laws work both ways, so why is this impossible? The answer lies in probability. There is only one way for a glass to be whole, but countless ways for it to be broken. Nature trends toward chaos. From the smallest atom to the expanding universe, everything is in motion, following the path from order to the vast unknown. Let us imagine a brand new deck of playing cards. When you first open it, the cards are arranged in perfect order. All the suits follow each other neatly from ace to king. This arrangement is very special. There is only one way for the deck to be perfectly ordered. Now suppose you shuffle the deck. After one shuffle, the cards are mixed. After 10 shuffles, they are completely random. Now ask yourself a question. If you kept shuffling that deck for 1 billion years, what are the chances that it would accidentally return to its exact original order? Technically it is possible, but practically it is almost impossible. The reason is simple. There are countless ways for the cards to be mixed up, but only one way for them to be perfectly ordered. Nature follows the same principle. Scientists call this idea entropy. Entropy is simply a measure of how many different ways something can be arranged. Ordered states have very few possible arrangements. Disordered states have many. A glass sitting neatly on a table is an ordered state. The glass has a specific shape, and the water is contained inside it. But once the glass falls and shatters, there are millions of ways the pieces can scatter across the floor. That messy arrangement is far more likely than the neat one. Because of probability, the universe naturally moves from order toward disorder. Not because there is a force pushing it in that direction, but because there are vastly more ways for things to be messy than for them to be perfectly arranged. This gradual increase of entropy gives the universe its sense of direction. It gives time its arrow. The past had lower entropy. The future has higher entropy. The Big Bang itself was an incredibly special moment in which the universe began in an extremely ordered state. Like a brand new deck of cards, ever since then the universe has been slowly shuffling itself. Stars burn fuel and release energy into space. Planets form and break apart. Living creatures eat organized energy and release heat back into their environment. Even life itself is part of this cosmic process. When you eat a meal, your body takes organized energy stored in food and converts it into motion and heat. You are constantly transforming order into disorder. In a way, every living organism is a small engine in the great thermodynamic story of the universe. This process will continue for an unimaginably long time. Eventually, stars will burn out. Galaxies will grow dark, and the universe will approach a state of maximum entropy, sometimes called the heat death of the universe. But that moment lies trillions upon trillions of years in the future. Right now, the universe is still full of motion, energy, and transformation. The atoms in a glass of water are still dancing. Planets are still orbiting their stars. Galaxies continue drifting through expanding space. And as long as this motion continues, the story of the universe is still being written. So the next time you look at something that appears perfectly still, a quiet glass of water, a silent night sky, or even the ground beneath your feet, remember what physics has revealed. Stillness is only an illusion. Behind that calm surface, the entire universe is in motion.